Um, so hi everyone. So welcome for for take two of the lecture 22 on Markov chains. We tried recording it at some point earlier today during the regular time, and there were a bunch of technical issues with Zoom. So we're gonna just start over again from the top. So the topic today is going to be in Markov chains, which is kind of this like fundamental this fundamental concept within mathematics. And so we're going to kind of describe how this gives an understanding of graphs, right? So it's the Markov chain is a more kind of more powerful object that has extra conditions. And the goal today will be saying, well, how can we derive many types of Markov chains from graphs, and then what are the conditions under which this precisely models some property of the graph? And then this is a nice way I like to interpret graphs because it ties into the linear algebraic way of thinking about them. And so and which is, and you can think of them statistical and linear algebraically, which ties in with a lot of the ways other things we talked about in this so far in this course. There are other ways also of thinking about graphs. This way is particularly appealing because it maps to PageRank, which will be the topic of the next lecture. We'll talk about different ideas on graphs, on where so the PageRank often is associated with the web graph, but applies many other places. We'll talk about social networks as another instance of large graphs and how to think about them. There are many other very combinatorial different ways of thinking about graphs as well that come up in data mining. We're not going to so much cover those within this class, although a little bit in the last lecture. And then we will, but these ideas will carry over to other things in these main topics. But this will be the main focus for us. All right, so let me start by sharing my screen. Oh, okay. Yeah, so great. So yeah, so that thing off there. Okay, so to kind of, we'll be going through a lot of definitions and try and kind of spice it up a little bit. We're going to talk about some life lessons you can learn from Markov chains. One is, and we'll see how these kind of, how the things kind of fit in. So the first one is only your current position matters. Going forward, don't worry about the past. Let me get this off of here. So the second one is you only need to worry about one step at a time. You'll get there eventually, or maybe you won't. And then the third one is in the limit, everyone has perfect karma. All right, so we'll kind of see these this time throughout the lecture. Okay, so we're talking about graphs. And so we saw graphs before, and this is the same example we used when we talked about spectral clustering, which is the goal then was to find a way to cluster the nodes in the graph, the vertices of the graph. And that was kind of using the edges in order to do this. And so what was important and useful about this is that you could represent it by picture or by the vertices and the edges. But what was nice is this kind of graphical representation where you can say that by the adjacency matrix. And just to quickly recall, this meant that if we considered an edge between C and D, then I can say C is connected to D, and there's a 1 here. Okay, but this is symmetric. So if I looked at D and C, that is also here, right? So this does not have a direction on the edge in this case. It's going to be the same in both directions. Today, we'll talk about ways where you can have a direction on the edge, and then you don't necessarily need to have the symmetry. So it only go in one direction. From C to D, it would have a 1, but maybe not on the other direction. Also note that if I take some other edge, say G and H, and I go from G to H, there is a 0 here because I don't have an edge here. So this is not an edge, so it has a 0. Right? And so this gives rise to this adjacency matrix, which we see over here, which is just all these 1s and 0s. And this will be the starting point. Okay. But when we deal with the Markov chain, it's not exactly the same as just starting with the graph. We're going to have the same kind of node set here. I'll use vertex and node kind of interchangeably in the lecture, and this V will be the same. Okay, so it's going to have 3 components. This is the vertex set. Okay, it's going to have a matrix, which is going to be down here, is in the same example, which is the probability transition matrix, which is similar to the adjacency matrix, but I've added one thing in that for every column, if I look at every column here, I've normalized it so that I've taken the adjacency matrix, and this represents of node B has 2 edges to A and C. So that's the 1 here and the 1 here, but I've divided by the total number of nodes. So I divide everything by 2 inside of each column. Okay, so that's saying I'm at node B and I want to know I'm going to transition. It basically is modeling if I'm at node B, I'm going to take a 1/2 probability to D. That's this one here, and a 1/2 probability of walking to A. So if I just have the structure of the graph that's given to me, I can convert it into this probability transition matrix where I assume that at a node, if I randomly walk around this graph, what I'm going to do is I'm going to each point pick a random edge and randomly walk on one of those edges and make it uniform, right? So B has 2 2 edges. So it's 1/2. If I look at another one like E, it's got 1, 2, 3 edges. And so A, B, C, D, E, right? Then it has 1/3 probability of going to C. It's got 1/3 probability of going to F and 1/3 probability of going to G, right? And then in the case of, say, like H over here, then there's only one option to go out to F, and so this isn't, it's already normalized. Okay, great. So we've got this Markov chain, and okay, so this covered 2 parts. This described the vertex set, which we get from the graph, the probability transition matrix, which is also can be derived directly from the graph. We can also, if we have different information like directedness information, so it's not symmetric, notice the probability transition matrix is already not symmetric because it could be normalized in different ways. So yeah, for instance, this 1/2 and this 1/3 are going to be, sorry, not this 1/3, this 1/3 here. These both correspond to D and B. This edge right here, it's 1/2 from B to D, but 1/3 from D to B. So it's not symmetric already. But if we had different symmetries, we wanted to different kind of weights and probabilities we wanted to encode, we could easily directly encode them in the probability transition matrix. So we have more power over the kind of the information on the edges and the graphs we can encode. Okay, but there's a third component to every one of these probability to these Markov chains, and that's this Q, this initial state. Okay, and so this is not inherently part of the graph. Okay, and I have two examples of this initial state here. One is a vector here, which is 0, 1, 0, 0, 0, 0, 0, 0, 0. Okay, and what this says is that my initial state is always in B. My initial state's in B. Okay, but or it doesn't need to have this thing where the state is only in one location. The state could be like this one instead, right? And what this one is saying is I'm 1/10 in A. Okay, that's this one. I'm 3/10 in D, and I'm 6/10 in this would correspond with F in F. So my initial state is now not just kind of a single location, but is a probability distribution of these locations where I could be. And I could start out this way, and we'll see that in a number of the kind of approaches to analyzing this we will consider, we will actually be generating these probability distributions over states as the kind of internal representation of what's going on here. Okay, so we have this initial state, and a Markov chain has this node set, the probability transition matrix, and then also the initial state. Okay, but if we want to analyze a graph, this initial state doesn't really have a place in the graph. Okay, but let's kind of see what the Markov chain is doing, and then we'll see how can we get rid of this initial state. So we're just talking about the graphs. Okay, so let's start with an example. And so I've started with the same probability transition matrix here, right, that we had in this example, and this initial state, which is basically in B with probability 1, right? But after one step, so I'm basically starting here, and after one step, half the time I go to A and half the time I go to D. And so my state Q1, after one step of this process, and this is kind of describing a process that proceeds in steps, now my probability is 1/2 in A and 1/2 in D, just as this column is telling me, okay? But then if I keep going in this process, now I want to get to a second state instead. And remember, I had 1/2 in A, and I had 1/2 in D. This was my state after step Q1 here. And I do this again. I send 1/2, well, I split that into 3 pieces to A, B, and C. And this other 1/2 from A, I send to 3 pieces into B, C, and D. And I add those up. I get 1/6 in A. There are 2 components. There are 2/6 in B, 2/6 in C, and 1/6 in D. Okay, so I can repeat this. I can also think of applying this directly, the probability transition matrix twice on my initial state here. That's another perfect interpretation. Or I can take this whole matrix here, right, a whole probability transition matrix, and I can square it. I can think of combining this together. I've taken this term and I've applied this first, and I get this p squared matrix, which is just p squared, and I can just apply that once. That describes the process of doing this step twice, but inside of a single matrix. Okay, so the order of operations within matrix multiplication or vector matrix multiplication, you can multiply things in any order. Sometimes it's computationally faster in one way than the other, but you can combine them. I can either combine Q, here first, or I can do the p squared part first. Okay, and I see this mass is distributed, but I can only get to steps A, B, C, and D with different probabilities. I do this one more step. Now this kind of I started with 1/6, 2/6, 2/6, 1/6, and this spreads out even further. And notice that kind of, for instance, what's new is this 2/6, 1/3 of it is going now to E, and so now I have this factor 1/9, which is winding up in E. Yeah, so that's yeah, so that's 2/18. Yeah, that's what's going on. 2/18 is 1/9. Okay, so it's spread out further still. After 3 steps starting in B, if we go back to original graph, you see you cannot get to F, G, or H yet. These are still 0 probabilities. Okay, so the big question you should be hopefully is coming to your mind is we can keep doing this. Can we say something about in the limit this vector Qn, right? Let's say lim as n goes to infinity, what's happening, right? We can think of either combining this into a single p to the n, like this whole huge number of times, or just applying this over and over again. What's going to happen when we keep applying this? And this seems like a nice quantity to kind of understand. Where is the distribution? Okay, so the first point to make, which we'll go and see later, is this is not uniform. Okay, in the limit, it will not necessarily, there's no reason for it to be uniform 1 over n everywhere. Okay, but the bigger issue is we cannot always define this notion of a limit. So for certain kind of processes, we don't always have a limiting distribution. And so in order to use this tool, this idea of, look what, if we do this random walk and do it for a long period of time, this will, as we'll see kind of next lecture, this will say something very fundamental and important about the graph, which is modeled by this Markov chain. But it doesn't, we can't always, this limit does not always exist. Okay, so we want to talk about, oh yeah, and so this first life lesson, only your current position matters going forward. Don't worry about the past. We only need to worry about going forward, and we will kind of, that's where this Markov comes from. A Markov process is something that only maintains a state, and the next step only depends on that individual state. Okay, great. Before we talk about what's going on here, there are 2 ways to think about these Markov chains. Okay, so the first way is that we kind of only consider one possible location at a time. Okay, so we're only in one state at a time. We're not thinking, this is not this probability distribution we were mentioned earlier, but this is like this example, e.g., where Q was 0, 1, 0, 0, 0, right? So we only have this one position at a time and say, I'm at position B, that's it. Okay, and so this corresponds with a random walk around the graph. And there's the probability transition, tells us how we do this random walk, and we think about going from one step to the next. It's kind of like a discrete automata you may have seen in a different an earlier computer science course. Okay, and then the other one, which we were kind of looking at before, is we have a probability kind of distribution on states. Okay, and so this corresponded with the example of Q equals, say, 1/10 in A, 0 in B, kind of 3/10 in C, 0, 0, say 6/10 in something else, right? So there's a distribution of where we might be, and we can kind of maintain this distribution or think of moving this, pushing this distribution through as we're analyzing this. Okay, and so a lot of places where Markov chains are taught, there are they're actually oh yeah. So they're only they only teach kind of one view of these two views of the Markov chain, and they're kind of different algorithms you'll do to work with both of these different views. The first one comes up a lot in Bayesian analysis and came up in statistical physics, and we'll see that towards the end of the lecture. And the second one is turns out to be more linear algebraic, and we'll mainly focus on this. And this will actually correspond with a lot of what is done with PageRank, which you'll see in the next lecture. All right, so okay, so what we want to largely talk about is we want to talk about this property called ergodic. Okay, we say a Markov chain is ergodic if let's say if there exists some time t, which is which is like the number of time steps we've taken so far, so that for all n greater than t, then q of n, so that's we've maintained this distribution over the states for n steps. So for all values of n greater than t, that if I look at all the entries in this vector, it's strictly greater than 0. Okay, so after a time t, every possible node in the graph has a positive probability that I might be there on the random walk. Okay, it can't be that for some time in the future I might be there. It has to be for every node, for every time in the future I have a chance to be there. Okay, so this is what it means to be ergodic. And if I have this ergodic property, then I can talk about the limit. Okay, so this definition is actually pretty nuanced, and it's kind of, if you look at a Markov chain, you're like, is this going to be the case? That's kind of hard to decipher. So we're going to talk about instead kind of how to define this. Is this is true if not one of, so this is a Markov chain is going to be ergodic if not any one of these three conditions hold. If it's going to be cyclic, if it's going to has absorbing and so transient states, okay, and if it is disconnected, okay. And so I'll define, so it's easy to think of if it's ergodic if it does not have any of these traits. If it has any of these traits, it's not going to be ergodic. And so it's easier to define this and to understand it by understanding these three traits. So next I'm going to kind of define these three properties and basically define them through examples. Okay, and if it doesn't contain any of those properties, then it has to be ergodic, and then we can talk about the limits and this nice property. And this will guide us, and this will be important in understanding why PageRank actually works the way it does. Okay. Okay, so the first is that kind of a Markov chain is going to be cyclic if there's kind of these classes of states where it does, it kind of cycles between these different classes. So if I start in one set, then it will hit that in after some fixed number of these other sets. So I think this is much easier just to see by example. Here are three probability transition matrices which totally encode these cyclic Markov chains. The first one is, it has two states, A and B, and just says that with probability 1, if I'm in A, then I transition to B, and if I'm in B, I transition back to A. So if I start in A, then on step 0, then every even step I'm in A, every odd step I'm going to be in B. Okay, the next one has 3 states, A, B, and C, and it says A always transitions to C, C always transitions to B, and B always transitions to A. Okay, so with probability 1 every time, and this is going to be cyclic. Now it has 3 states instead of 2 states. So every kind of thing divisible by 3, if I start in A, will always be A, and off by 1, it's C or B. Okay, you know, it can be more general, like in this case, where now I have 2 nodes A, B, C, D, E, and F, which I think are on one side of a graph, and B, C, D, and E are on this other side, and this makes what's called this bipartite graph, where A has a 1/4 probability of going to each of these states. Okay, and the same thing with F. It can only transition to these states, but not A. And if I go back in the other direction, B can only go to A or to F. C only to A or to F. D only to A or to F. And this is looking kind of messy, but so it's only going back and forth between these 2 classes of states. So it has, you know, right? So A and F only go to these states, kind of B, C, D, and E, right? And so these are the only are the only possible kind of transitions, and so that there are only 2 real states that it can possibly be in. Kind of 2 classes of states can be in it, alternates between these. So it starts in one side, then it has to move to the other side and back and forth, right? So if it has the cyclic example, then the Markov chain is not going to be ergodic. All right. Okay. So the second type of thing is going to be if there are states which are, and so there are other things to keep in mind. If there are other things that mixes in between these states, like even if I had some edge from B, this is not the right place to put an edge, but like if I had a probability of going back to B that was say 0.001, and this was actually instead 0.999, right, of going to A, well, that's going to eventually mix together, and I don't always have to go back and forth between A. I might get stuck in B. Yeah. Anytime I touch something else, that recording box pops up. Okay, great. Okay, so okay, so now I have these absorbing and transient states. Let's look at an example I have here. I have A and I have B, and what's happening is for A, half the time I have a self loop, I stay back to state A, and half the time I go to B, but B always goes back. But B what is B doing? B always stays to itself with probability 1. Okay, so what's happening is if I start in A, this is what's called a set of transient nodes, because if I start in A, I can't, and I leave to go to B, then I can't ever get back to A. So then B would be this part of an absorbing set, because once I get to B, I never get out of this set. And this is an example with only 2 nodes, but you know, you can have a more kind of, let's jump straight to this more complex example here. So I have A and B, and A half the time goes to B and half the time stays to itself, and B half the time goes to, or this is, I guess, 49 out of 100 goes to itself, and half the time goes to A. But then there's this other set of let's see, of C, D, E, and F, and these guys kind of all mix, you know, to each other, right? They're all kind of uniform in here, and B has 1 out of 100 times this goes down to C. So 1 out of 100 times. And so now I've got this bigger example where A and B here, this is transient, and C, D, E, and F is going to be absorbing, because there's no way back from the absorbing set to into the transient set. I can go from the transient set into the absorbing set, maybe only with 1 out of 100 times I'm actually in B, so it's a pretty slow leak. But if once it leaks out, it can never come back. So this is a weird issue with the limiting case, is that maybe you can have different absorbing sets, and you might get stuck into this one instead of that one, and there are kind of these issues that you don't necessarily have a limit, or A and B don't have any mass in the limit. Everything leaks out of it. So these are also cases that we're not interested in so analyzing. Okay, and then the third class of these is these unconnected examples, and this is hopefully pretty simple. This one is A and B, where A always goes to itself, and this is B always goes to itself, but you can't get in between A and B. You know, it can be more complicated. In this case, I have A and B. These can go back and forth to each other, but then there's also this node C, which is a self loop of 1. So depending on where my starting state is, if I start all the way in C, then I don't end up in A and B. If I start in A and B, then I end up in just those, but never in any C. Or if I start with the distribution across them, I basically keep that distribution, which is fixed because it's not connected. Okay, and you can think of more kind of complicated examples as well. All right, so these are these 3 classes: the cyclic graphs, the ones with absorbing and transient states, and the one with which are not connected. And if you have real-world graphs, these sometimes have these properties, and we'll see next lecture ways that this can effectively be fixed by kind of doing some minor surgery on how we model these things, and that helps actually making it more stable as well. Okay, but these are kind of the properties, and so if the Markov chain is going to be ergodic, then what that means is that we can now, I'm not going to explain, why we can always do this, but it means we can now think of this in the limit. And so we can think of p to the n as n goes to infinity. And this is going to be this probably transition matrix p star. Okay, what this p star is doing is this is saying in one kind of step, p star, pushes the state to the kind of the final state where it's converged to. And so for any starting position q, right, we apply this p star matrix, which is the limit of multiplying by p over and over and over again, and to get this pn, and this gets us to q star. Okay, and this q star is now this vector. So so this q star kind of is a vector, and it has some weight for each node. Okay, so this will be q star j is for the jth for the jth node, and this tells us something about how important that node is going to be, and we'll kind of keep exploring this, right? But if it's ergodic, we can then define these quantities. I couldn't necessarily define them unless we knew it was going to be ergodic. Okay, so what are some things we can say? Okay, yeah, so this is life lesson number 2. You just need to worry about one step at a time. You will get there eventually, or you won't, right? And so, you know, if you won't is if it's not going to be ergodic. And so this is the idea of you just kind of keep kind of iterating this process, and you eventually will get to this converged 2 state, which is what we're after. Okay. All right. So what are some properties about this, right? Okay. So the first observation I want to make is that I can say, if I take this state I've gotten to after q times p star, right? And this is going to be the state q star here, and I multiply it again by another matrix P. So I apply this probability transition one more time, just the original matrix, not the P star matrix. I have to get back Q star, right? Because this is in the limit. I've done this infinite number of times. It's going to be stabilized there. Okay. But what this means is I can actually replace this term, this P star Q, with Q star, and I get this expression here. Okay. And so this means, this is very cool. It means that Q star is an eigenvector of P. Okay, so this is the property of eigenvector. I multiply a matrix by a vector, and I get back some scale multiple of this vector. It turns out it's always the top eigenvector, right? So I'm going to have them in some sorted order. This is the one corresponding, let's say, the largest kind of singular value that we talked about in like dimensional reduction. Okay, so the top eigenvector, the most important one, is going to be this Q star state. Right, so this gives us one algorithm. We'll talk about algorithms to compute these kind of more formally, but this gives us one way of computing it, and it says it's equivalent to the top eigenvector of the original matrix P. It's also the top eigenvector. I could put P star there. It's also the top eigenvector of P star, as it turns out. But we don't want to necessarily have to compute P star. We can just take P, take the top eigenvector. That gives us Q star, which is pretty cool. Okay, and it also has these other properties where there's this property called that's called like the delicate balance. And so what this is saying is that in this final configuration state where we have this probability distribution over, if we took this random walk forever on this graph, then the probability of being in some state I, and then applying the probability transition matrix to go from I to some state J, right? So I've got some state I, right? And I'm in here with some probability Q star I, and I have some probability of transitioning to state J. Okay, so I want to look at, given that I was an I, and I do this kind of one step, right, according to my original probability transition matrix. Okay, so I'm probably being there and I take a step, I'm in state J. Well, this is going to be balanced. This is going to be equal to the probability I'm in state J in this distribution, and I take one step from J back to I, right? So, you know, this is true in general that all these kind of, I take one step and I get the whole probability back, but this is true on individual levels as well. So I can kind of just look at two states and know that they somehow have, I know what the probability transitions between them are, and I know that they have to balance in some way. And so I could solve kind of some kind of linear system in this way to solve it as well. But this is a kind of cool property that when you're analyzing things, this kind of says, oh yeah, this is why this has to make sense. Okay, so there are lots of these cool properties that come out of kind of thinking about the structure of the converged to state of the Markov chain. Okay, let me see what else I want to say. Yeah. Okay, yeah, so this is in the limit, life lesson 3, everyone has perfect karma because you trade off with everyone else, and that's the, you converge to amount of karma you have, as much as you give, you're going to get back. Great. Okay. Okay, so I want to talk about yeah, so yeah, so I think I said that right. So let's say, okay, but before we talk about algorithms and what are the algorithms associated with this, there is a clear, there's this limiting state, this Q star. I just want to highlight this is not a uniform distribution. If it was uniform distribution over 8 nodes, everything would be 1/8, right, in all these values. But this is the actual limit on this example here, right? For A, yeah, so for node A here, this is 1, this is like 3/20, and that's going to be similar for kind of for A, for D, for C, for E, and F. These are nodes that are kind of more central in the graph. All of these have probability of being 3/20. That's these values here. But these nodes which are not quite as central in the graph, kind of this state B and this state G here, these are probability 1/10, right? So these are lower probability of being these nodes, and then the ones kind of out on the fringes, H, this is only 1/20 probably being there. So if I'm doing, so think of this, if you're doing a random walk around the graph, and every time you're at a node, you look at all the edges I have available and I pick one at random and do that, I'm less likely to be out here in the fringes, because if I go out there, then I have to go back right away, and I might not walk back there. I could instead go and see the rest of the graph. Okay. Kind of, so it's not a uniform distribution here because I'm less likely to be in the edges. I'm more likely to be on these more central important nodes in the graph. Okay, so that's kind of what this is capturing here. Right. So okay, so our goal kind of with this, there are other ways to analyze, use Markov chains, and like something like the second eigenvalue tells you how fast it mixes, and this is important for understanding various algorithms. We want to say, talk about algorithms for computing Q star, right? So I want to compute Q star, and if you haven't noticed, we've already talked effectively about, explicitly about 3 of these algorithms, and we'll say the fourth one as well. Okay, so the first algorithm for computing P star is to take the eigenvalues of P, right? So say the top eigenvector, we'll call this V1 of here. So we compute the eigenvalue decomposition. We really only need the top one, so you can maybe just run some internal command inside of Python or MATLAB or something like that. You get out V1. Now V1 is L2 normalized. This is a unit vector. So we need to turn this into a probability distribution. So then to get Q star, we simply say it's V1 divided by the L1 norm of V1, right? So if you remember, L1 norm of V is going to be the sum over j from 1 to n of the absolute value of kind of these terms. So we add and we normalize by this, and then it becomes a probability distribution, which is what we want for Q star. Before we were dealing in these unit vectors, which had an L2 norm. but now we need this probability distribution here. Okay, so this is the first simple algorithm. This is a very linear algebraic approach to it. There are other kind of things we can use linear algebra. Okay, the other way we talked about is that Q star is the limit as we do P times, well, let me first write it this way, is P times P times P up, P times any initial state Q0 here. So I start with initial state Q0, and I multiply these effectively n times for some sufficiently large value of n. This is going to converge towards this, this Q star approach. And so there are two ways of splitting this. The obvious way to do this is to kind of, and this turns out the right way, is to do, think of this as a for loop for I equals 1 to, let's call this m, because I've been using n as the number of nodes. I'm going to say qi equals p times qi minus 1. Okay, so we start with q0 and we do this, and kind of we'll return q star equals, is approximately equal to qm after m steps of this, okay, for some sufficiently large value of m. Okay, so this is, you want to do the vector matrix multiplication. This turns out to be faster than a matrix multiplication. I could have done this computation first, and then these other ones, right? So this is kind of the third algorithm, which is closely related, which is q star, I guess, these are approximately equal to, and effectively the eigenvalue, the way eigenvalues are computed, they're probably approximate as well. But this is basically qm. So I pre-compute this qm for some sufficiently large value of m times any q0, some initial state. Okay, so I've pre-computed pm, and I could do this, which is just the product of I equals 1 to m of this matrix P over and over and over again. There are ways you can think of decomposing this into, I can say, equals to, say, Pm divided by 2 times Pm divided by 2, right? And then I can say Pm divided by 2 is equal to Pm divided by 4 times Pm divided by 4. So I really only need to do log m of these matrix multiplications if I'm approximately, if I'm clever about it. But the matrix multiplications are typically much more than the matrix vector multiplication. So step 2 is, version 2 is typically faster. Okay, so these are 3 algorithms that we've basically seen before. I'm just spelling them out. The fourth one we've talked about, which is a random walk. Okay, so we want to now explicitly do this random walk, and this is one where we maintain an explicit state. Okay, so we think of Q as being 0, 1, 0, all zeros here, and this is basically, it's in state, Q is kind of is in state B. Think of, we have this graph, we have these nodes, and the state is always exactly at one node, and then we do this random walk around the graph. Okay, so for each step from, so this is, so each Q is in this node set, and so I'm basically at some node, and I move to a neighbor on an edge, and this is VI, and I move to VI plus 1. Okay, and then I just repeat this over and over again, and so in the output, I then collect the set V1, V2 up to Vm for some large number of steps I've done here, and so these these V1 through Vm gives me this I can imply a probability distribution. So Q star of J, for instance, equals the number. Let's call this set S. It's the number of V in S such that V is equal to J, and I divide this by M, right? So I get an estimate for Q star for each value by just looking at the number, the sample estimate of the number of times I'm in each of these states. Okay, so I just physically do this random walk around here, kind of mechanically walking around this graph. There's kind of some nuances in how to do this. This is used a lot in kind of these Bayesian formulations where I have this kind of posterior I'm trying to estimate from, and there's some issues that two states next to each other are kind of correlated with each other. And there's some worry about this. And so without going into too much detail, so you usually do a burn in kind of period of, say, roughly 1,000 steps. And this is usually roughly what is used. And then collect the next roughly 500 steps. Okay, so what can happen is if you end up accidentally starting your initial state in like some weird corner of the graph, then you're going to bias towards there at the beginning, and this will affect your overall probability distribution. So I want to first do this burn-in period where I randomly walk around the graph, and hopefully at that point I'm at a sufficiently random spot, basically according to the Q star distribution, which turns out to be okay. And then I collect the next 500 states and use those for my sample estimate. And this one hopefully is kind of unbiased. Now, it's still not totally unbiased because two kind of neighboring states here are going to be correlated with each other. And so typically you can think of this as maybe on, depending on the structure of the graph, equivalent to maybe 1,000 samples instead of 500, instead of 5,000 samples, because there's some autocorrelation between them. So I don't quite have all the variance guarantee I'd get with the 5,000 kind of completely uniform samples, but this typically thing works. Kind of in theory, you're supposed to take 1,000 steps, take one sample, take another 1,000 steps, take a second sample, but this typically takes so long, and this is not what's done in practice. Okay, so this is the fourth way, this random walk approach. So great. Okay. So these are the algorithms for computing Q star, and you're going to be doing these in your homework. This is what your homework will be doing. They're all very, very pretty simple algorithms to do. The random walk, you have to implement a probability distribution, but you've done that for k-means plus and maybe something else before already, so that shouldn't be too hard. Okay, so I want to conclude by quickly talking about this alternative view called this Metropolis algorithm, which kind of is looking at this random walk approach where I'm maintaining an explicit state. And this is by these 5 authors from 1953 around, it's invented in the work and trying to create is part of like the Manhattan Project, or as an outgrowth of this, where they're trying to understand these physical systems that were too complex. They couldn't derive what was going on, and they want to understand the energy of these systems. And they had some energy of some state, and this is a continuous state space that they're working with. So they had some energy of some state, and they wrote this as E of Q. And they kind of said, okay, it's understood that to understand the energy of the state, the probability that abilities say that a particle is in Q should be roughly proportional to some weight Q, which is going to be E to the negative energy or something like this. They have some formulation that looked like this, where they could say, I know some weight which is proportional to the probability. I can evaluate at any given state, but I can't actually, I don't know how to normalize this. So I don't know the actual probability. I just effectively have this likelihood. How do I get a samples from this probability distribution? Okay, and so this is what the Metropolis algorithm is doing when it's given these weights and wants to get a sample from this distribution within Bayesian analysis called Markov chain Monte Carlo approach. Okay, and so let me just quickly write down the algorithm, and then we'll kind of explain what it's doing. So now what's happening is I've got this Markov chain, and if you remember, this has three components: this node set, this probability transition matrix, and this initial state Q. And so I'm going to now this node set is going to be something that's continuous instead. So think of this as being RD, or a subset of RD. Okay, so it's continuous state space now, and I want to draw samples from it. But P, I don't have an explicit matrix anymore. It'd be an infinite dimensional matrix. I can't write this down. So this is instead going to be an algorithm. Okay, and this Metropolis algorithm encodes this algorithm based on, and this is kind of based on these weights W. Okay, so I have these weights W associated with everything in there. Remember, this portion of the probability I want to be in there. Okay, and we'll describe all this step through this algorithm. And then I have this initial state. I need to initialize this somehow. And remember, this is now not a probability distribution, but this is state V0. This is one of the possible states. This is an element of RD here that I'm working with. Okay, so then what do? We have some kernel function which goes from V and generates, think of like a Gaussian kernel. And I have the state V, and I want to generate some potential neighbor kind of nearby. And it doesn't matter what this K function is, but think of, I will select some U, a proposed next location somehow in the neighborhood. Usually you'd use like a Gaussian kernel, which you can generate easily, even in high dimensions, right? So I can generate data from a Gaussian kernel, and I make some step. Okay, and then if the weight is larger at U than it is at the previous state, VI, then I'm going to set, the next state, VI plus 1 to U, right? So if the weight is larger, then I set this to VI plus 1 is here. If it's not larger, then this value is going to be less than, or this is less than 1, right? The weight of U over weight of VI, this is now is less than 1. So I still might select U as this next state, but with some probability. If it's not that much smaller, then yeah, I'll still make that step. I'd rather be in these high weight states. These correspond with low energy, and they're more and more favorable in some way. So I'd rather be in these lower weight, I'd rather be in these large weight states. If it's lower, but not too much lower, I still might move there anyways. But if I don't do this, I flip a random coin and I don't move to U, then otherwise I move, the next state is in the same spot. I don't move again, and I have to try this over again. And so ultimately I collect this set of states here, V1 through Vm for some large M, and then I use this as a sample from my distribution. Okay, and so this, you can show that in the limit, this converges to the right distribution. There's a lot of work, and it's kind of a little bit mysterious and hard to grasp when it actually works. How fast it converges has to do with the second eigenvalue of some infinite dimensional Markov chain and all this stuff, but it will eventually converge as long as it's kind of connected. You guarantee it's not going to be cyclic or absorbing in transient states in here because of this step. There's always some probability, as long as the weights aren't 0, and the neighborhoods are connected with each other. Okay, and so there's some issue that sometimes I'm in exactly the same state 2 times in a row. But it turns out that in the limit, this is okay, but I need the sample to be big enough to kind of get rid of these effects. So yeah, so this is all I want to say about Markov chains. We'll see a very powerful way that they're used in understanding graphs for PageRank, for understanding the space of web pages, the web graph, and kind of other stories about how search engines work in the next lecture. So I'm going to end here unless there are any questions. So great. So the one audience member does not have any questions, so we will stop here. So thanks for joining, and so stay safe out there.